You might think snow is pretty straightforward. It's just ice crystals that become flakes under the right conditions in the atmosphere, then fall from the sky. But all sorts of stuff can lurk inside snow, from single flakes to inside massive ice sheets. So to reveal snow's hidden layers, let's take a look at why those layers are always flat to begin with.
We're told that every snowflake is unique, that every single one grows slightly differently to produce one-of-a-kind, six-pointed forms. But these are crystals growing in 3D space. It seems like they should be able to grow in any direction. So actually, when you think about it, why are they always flat hexagons? Why are snowflakes basically 2D? It all comes down to how ice crystals form on the molecular level. The most important condition for determining what shape a snowflake will take is temperature. Different temperatures generally correspond to different shapes. Between about -10 and -22 degrees Celsius, you're most likely to see that feathery six-pointed shape known as a dendrite. But snowflakes aren't always flat. Depending on atmospheric conditions like temperature and humidity, they can form columns, rosettes, needles, or any number of shapes. Between -3 and -10 degrees, they might form hollow columns or narrow needles. But the most basic snowflake structure found at a wide range of temperatures is a flat hexagonal plate rather than a flowery dendrite. We don't know exactly why temperature has such a drastic effect on the shapes of tiny water crystals, but we do know that they're relatively 2D. So why is that? The six-sided symmetry of those simple plates is a direct consequence of the structure, the molecular structure of water. Water molecules have what chemists call a bent geometry because it looks like it's been bent in half. You've seen pictures. Water is also polar, meaning that one end of that bent molecule, the oxygen, has a slight negative charge to it, while the two hydrogens are slightly positive. This means that when water molecules come together to form a solid, they will line up so as to match positive and negative charges, oxygen to hydrogen, which naturally lends itself to a hexagonal shape as all the bonds align. This feature of crystal growth, where the availability of chemical bonds dictates the larger structure, is known as faceting. Depending on the conditions, water molecules might grab the edge of the hexagon more easily, making a thin plate, or the face, meaning it will grow into a column. This odd effect is known as sharpening. Now, if that were the whole story, all snowflakes would have a hexagonal structure. But when conditions are right, those hexagons can start to branch out. This is where our other most important condition comes in: humidity. As a snowflake grows, the water around it is incorporated into the crystal, meaning in that tiny environment, there's less water, and water molecules have to travel a little farther to join the snowflake. But near the edges, water molecules don't have to travel as far, so they join the edges more easily and quickly, and sharpening, once again, leads to smaller structures closer to the edges of the snowflake. As the crystal grows larger, it also starts to grow faster as those molecules attach to the edges. And whenever conditions make it possible for a crystal to grow faster on its edges than its faces, the edges can get really elaborate, producing those dendrite structures. The conditions have to be just right for this to happen, but it's not just water that does it. Even table salt can form dendrites under the right circumstances. So we're lucky that the conditions are so often just right when it snows. It means that we get to enjoy the beautiful array of shapes we picture in a snowflake. Although other crystal structures, small ice columns falling from the sky, that would also be pretty cool.
So the shape that the outer layers form pretty much comes down to temperature and humidity. But that brings us to one super weird way the inner layers can form: around bacteria. Yep, there can be bacteria inside snow.
Clouds capture our imagination when we're kids. They look like fluffy cotton balls, and any Mario game would lead you to believe that you could jump around on them. Eventually, you learn that you would fall right through them, though, because they're made of tiny ice crystals or water droplets. Not only that, but it turns out that clouds are also chock full of bacteria. And those bacteria may actually be pretty important and play a role in precipitation patterns around the globe. For raindrops or snowflakes to form and grow big enough to fall to Earth, there generally needs to be something for the water molecules to start collecting onto, called a condensation nucleus. This can be a speck of dust or other inorganic stuff drifting around in the air, but sometimes a floating microbe will do instead. Some microbes can actually cause ice to form at warmer temperatures than inorganic particles can, thanks to special proteins that encourage the orderly arrangement of water molecules. We think these proteins on the surface of their cells can arrange water into strips of loosely and tightly packed molecules. This mimics the boundary between liquid water and air, where molecules are more likely to have space to form ice crystals in nature. When microbes act as condensation nuclei, scientists have a special word for it: bioprecipitation. And even though it's hard to study what's going on at the microscopic level inside a cloud, we do have some solid evidence that bioprecipitation happens. In 2008, researchers collected freshly fallen snow from a bunch of locations in Europe, North America, and Antarctica. They melted the snow samples and filtered out any tiny particles inside, and then mixed the particles into different samples of pure water to control as many variables as possible. Then, they slowly refroze each mixture, reasoning that a higher freezing point probably means that there were more nuclei in the sample. Basically, with more molecular help from the ice nuclei, water doesn't need to be quite as cold to form ice crystals. Then, they treated the samples to kill any microbes that were hanging around, and repeated the experiment to see if the freezing points changed. This gave them an estimate of how many of the nuclei were biological, and their math showed that there were around 4 to 120 nuclei in each liter of melted snow, most of which were probably microbes. Plus, microbes were in every sample, even the ones from Antarctica, and this suggests that they can travel really long distances in clouds, even between continents. And in 2010 and 2011, a researcher collected hailstones after 3 storms on or around the campus of Montana State University and analyzed their structures with more melting and refreezing experiments. He found lots of bacteria in the hailstone's cores, thousands per milliliter of meltwater, but almost none in the outer layers. In other words, it looked like bacteria were the seeds that got the hailstones forming. So clouds might be a helpful way to travel around, while acting as condensation nuclei gives bacteria a way to get back out of the atmosphere and to the ground. Scientists think that a lot of the bacteria that can do this are probably plant pathogens, microbes that cause diseases in plants. Their ability to get water to start freezing at higher than normal temperatures lets them make ice that ruptures plant cell walls so they can feast on goopy nutrients. Plants, in turn, release bacteria into the air along with the water vapor they produce, so microbes can get back into the atmosphere and keep the cycle going. Precipitation can also spur plant growth, which provides more food for the bacteria. One specific bacteria species found to do this is a plant pathogen called Pseudomonas syringae. Its specialized ice crystallization protein, INA-Z, is actually used in machines that make artificial snow for places like ski resorts. But bioprecipitation isn't limited to bacteria. Scientists think that things like fungi, diatoms, and algae could all act as nuclei too. And researchers are beginning to think that this microscopic life could have a bigger influence on global weather patterns than we expected. This is difficult to study directly, but more studies have been done in recent years that suggest that microbial condensation nuclei do have important effects on clouds and precipitation patterns in different regions. Turns out that these organisms that are too small for us to see are hanging out in rain and snow too, whether it's natural or in our man-made winter wonderlands.
That's how snow comes to be. But like with all things, it eventually comes to an end. Like the old glaciers of northern Canada. And what's left behind is pretty unique. Here's how massive ice sheets covered and shaped a landscape into dunes.
What do you think of when you imagine giant dunes of sand? Maybe like punishing heat, little water, and practically no life, basically a desert. But the northernmost parts of Alberta and Saskatchewan in Canada are not a desert. It's below freezing for half the year, and there's enough precipitation to sustain the world's 20th largest lake. And yet here, at a latitude of 59 degrees, lies the Athabasca Dunes. They're one of the world's northernmost dune fields and one of planet Earth's most unique habitats. Like much of North America, Athabasca sits on the Canadian Shield, a large expanse of nearly exposed bedrock. The shield formed during past periods of glaciation when huge sheets of ice covered what is now Canada and parts of the US. This ice basically scraped everything down to that bedrock. The dunes themselves date to the end of Earth's last glacial period, somewhere around 10,000 years ago. These ice sheets were mind-bogglingly thick. Comparable modern ice sheets like Greenland's can be 3 kilometers deep. And although we think of glaciers as just kind of sitting there, they're actually flowing like in slow motion. The material they scrape off, and by material I mean stuff like mountains, gets pulverized down to what's called till. As the planet warmed and the glaciers retreated north, much of that till was carried along for the ride. Think about how much water must have been produced by the melting of a kilometer-thick sheet of ice the size of Canada. Around 8,000 or 9,000 years ago, that flood dumped a deposit of till into a massive lake, and that lake receded, and it left behind what we now know as the Athabasca Dunes. And then the wind took over. As the ice sheet pulled back, cold air from the top rushed down and created powerful winds that blew in a southeasterly direction. This cold, dry air was key to slowing the growth of plants that otherwise would have stabilized the sand with their root systems. As the sand flew around, it didn't just pile up into nice, floofy mounds. Instead, it abraded any rock formations that somehow survived being crushed by the ice. This generated even more sand and broke it all down into smaller and smaller bits. Eventually, the climate warmed enough and the glaciers receded far enough that the winds shifted to a more northerly angle where they remain today. But by that point, there was already a lot of sand. Today, individual dunes can rise 30 meters high and stretch for up to 1.5 kilometers in length. For a region with such unusual geology, it might not surprise you to know that there's a bunch of interesting life, too. The presence of so much water has allowed for the development of an ecosystem that's pretty unlike what you would find in a desert. There are quite a few rare forms of life found here, and a concentration of specialist species not found anywhere else this far north. In fact, the Athabasca Dunes are home to 10 endemic species, which means that they are not found anywhere else on the planet. And none of them are giant sandworms, unfortunately. All 10 of these species are, in fact, plants, and they've evolved a number of adaptations to the unusual and shifting conditions of the dunes. Their outer protective layer, called the cuticle, is extra tough to withstand the constant abrasion of windborne sand. Many grow especially quickly to help avoid being buried under shifting dunes. And if that doesn't work, some grow rhizomes, which are secondary stems that sprout from the root system. Perhaps the rarest of these species is the Athabasca thrift. To avoid the dunes entirely, it makes its home on a compacted layer of pebbles and sand called gravel pavement. Another rare species is the large-headed woolly yarrow. This name sounds kind of ridiculous, but it refers to the hairs that covers its stem that help the yarrow retain precious moisture against the relentless wind. Another species, called Turner's willow, grows up to 4 meters tall to peak above the shifting sands. And if one of its thin, flexible branches does get buried, it can become the start of a root system for a new, cloned copy of the tree. Even its seeds are well adapted. Their lightweight and fine hairs help the wind carry them to new locations. Unlike a lot of unique environments, the Athabasca Dunes are actually pretty well protected. They fall largely within Saskatchewan's Athabasca Sand Dunes Provincial Park, which is accessible only by float plane. Of course, distance from civilization isn't much protection from climate change, but so far the populations of the dunes' most important species seem stable. Let's keep our fingers crossed, because there aren't that many lakeside snow-capped dune fields out there. In fact, I think there's only one.
So the yarrow isn't the only organism that lives in extreme ice-covered conditions. Humans can live in icy snow too. In fact, we made an entire city inside the stuff. Here's that story.
In 1959, the US Army started building a town in Greenland. It was named Camp Century. And while science wasn't its primary goal, Camp Century was the source of the first long ice core ever acquired. An ice core that opened the door to the history of Earth's climate. Oh, also, Camp Century wasn't built on the ice sheet, but inside it. Camp Century wasn't the only US base in Greenland, but it was the only one completely underground. And this was no cramped one-room burrow either. Camp Century had a barber shop and a theater and everything you would expect from a small city, all inside the ice. Generally around 8 meters beneath the surface. All that ice meant that even after the tunnels were completed in 1960, Camp Century was plagued by construction issues. Between the weight of the ice pressing down on every ceiling, the heat generated by both buildings and humans, and the movement of the ice itself, the whole base required constant upkeep. By the time it was just a few years old, about 50 people spent their days cutting through ice with chainsaws to maintain the tunnels and avoid collapse. in a base that only ever had about 200 occupants at most. And then there was the nuclear reactor. Camp Century was powered by the world's first portable nuclear reactor. It was designed off-site and built almost IKEA-style in Greenland so that the people in the camp didn't have to spend too much time tinkering. The reactor produced plenty of electricity, but it also made a lot of heat, compounding the problem of melting walls. Plus, it made radioactive waste, which was left in the ice when the camp was abandoned. But we'll come back to that. To the outside world, Camp Century was for research. The army wanted to study how to live and build in such an extreme, remote environment, because this was the Cold War, and everyone thought that the army might end up somewhere with famously murderous winters. But a team of scientists got to tag along too. It was, after all, the perfect chance to study Greenland's ice sheet. Ice sheets are made of years of snow piled on top of each other, with deeper ice being made of older snow. Air gets trapped between the snowflakes, air that scientists can use to find what the atmosphere was like when the snow first fell. They can see how much carbon dioxide there was at the time, for instance, or even if a volcano erupted and threw a bunch of ash into the air. But global temperatures also affect the amounts of certain isotopes, or atomic variants of hydrogen and oxygen. So scientists can use those elements to understand global temperatures when that snow fell and became part of the ice sheet. We've used ice this way since the 1930s, but Camp Century provided the first opportunity to dig more than a kilometer down into an ice sheet. And that ice core is its most lasting scientific legacy. It showed Earth's climate evolving over the last 100,000 years, with ice ages and warm periods right where scientists expected them based on other kinds of evidence. Because it's one long, continuous sample of the past, the Camp Century ice core showed that these other, more piecemeal sources of data were accurate pictures of Earth's climate. The data weren't quite detailed enough to show the effects of climate change, which also wasn't as pronounced then as it is now. But Camp Century's ice helped provide a baseline for future research. We now know from it and other ice cores that what's happening now is not part of any natural cycle. It's our fault. The core keeps giving, too. In 2019, one researcher used mud trapped in the ice to figure out that Greenland's ice sheet is probably around 1 million years old. But science wasn't Camp Century's main goal, because, again, Cold War. Camp Century was really built to test out a plan to dig hundreds of tunnels throughout Greenland and fill each one with a nuclear missile. Luckily for the world in general, the ice didn't cooperate. They'd dig and reinforce a tunnel to fit a missile, but then the ice would shift or melt and change the shape of the tunnel. And you don't want that happening with missiles in there. Once the army realized that, Camp Century was on borrowed time. With its tunnels falling apart around them, the tiny city was abandoned by 1967. They'd removed the nuclear reactor a few years earlier, but they left behind the buildings and diesel fuel and nuclear waste to be encased in ice forever. But the very climate change that Camp Century helped reveal has also put a much shorter timeline on that forever bit. Greenland's ice is on the move. Radar has shown that Camp Century is a couple hundred meters west of where it used to be. And while it's currently under even thicker ice than it was back in the day, that's changing too. In 2016, a team calculated that as Greenland's ice melts, Camp Century's waste will be exposed to the elements by around the year 2090. Maybe sooner if climate change keeps getting worse. That's not just nuclear waste, but other hazardous materials as well. The ice is too thick for us to retrieve anything right now, but we'll need to do it eventually. It's up to us to learn from this city buried under the ice, because as Camp Century helped teach us, that ice might not last forever.
A giant snow fort city? What could go wrong? Apparently a lot. But we're not alone when it comes to building ice and snow dwellings. Bats do it too, on a much smaller and hopefully more eco-friendly scale.
When playing in the snow, few things are more fun than building a fort. But building a shelter out of snow also turns out to be a pretty ingenious way to make it through the winter, because even though snow is cold, it's a great insulator. We're not the only species that's figured this out. A tiny bat that lives in Asia has also mastered the art of making snow caves. The Usurian tube-nosed bat is native to Korea, Japan, and parts of Russia. Adults max out at about 8 grams, less than the weight of 2 American nickels, and like most bats, they're nocturnal insect eaters. During the warmer months, these bats spend their days holed up in dead leaves or tree cavities. During winter, the region where they live turns cold and snowy, and in response, they dig out little bat-sized snow dens to hibernate in. The dens are pretty similar to the snow caves you might have excavated as a kid, and while keeping warm in one seems counterintuitive because, like, snow is cold, it's actually a pretty good idea. See, a lot of air gets trapped between snowflakes as they pile up. Freshly fallen snow is as much as 95% air. That air can't move around, so it doesn't transfer heat well, making piles of snow excellent insulators. So researchers think that Usurian tube-nosed bats dig out little cavities, curl up, and go into torpor, a state in which they drop their body temperature and slow down their metabolism to reduce energy use. At around 0 degrees Celsius, the snow isn't exactly warm inside, but it doesn't easily get colder than that either, even when the environment outside does. Also, most predators aren't rooting around inside snowbanks for food, which helps keep the bats safe during their period of hibernation. And since snow is made out of frozen water, the environment inside a snow den is pretty moist too. This means that bats don't lose as much water while they're resting and can easily grab a sip if they do wake up thirsty. Depending on the weather in a given year, it can be anywhere from a few days to 6 months before the snow melts and the sleepy bat is exposed, and then it's back to hiding out in a tree cavity. We only know about one other non-human mammal that builds dens in the snow to keep snug over the winter, and it's way at the other end of the size spectrum. The polar bear. But maybe other species do something similar and it's just that no one has noticed yet. In fact, it was luck that we learned about these snow dens. The researchers who described the behavior just happened to hear about some bats found in the snow and decided to investigate. Just goes to show you can learn a lot by following your curiosity.
As much as I like humans, it's way cuter when bats make their homes in snow caves than when we do. And snow isn't only home to cute, cuddly animals and us. Sometimes thunder lives there too.
If you imagine a blizzard, you probably picture lots of snow, bitter cold, wind, biting at your nose and ears. But one thing you probably do not imagine is thunder. Thunder is usually reserved for summer rainstorms instead, but every once in a while, thunder shows up in what seems like the wrong season, and when it does, it can be kind of terrifying. It's known as thunder snow, and it's one of the coolest, rare quirks of weather. It's easy to think of winter snowstorms and summer rainstorms as pretty much the same thing. It's just different temperatures and with different kinds of precipitation. But there's a lot more to it than that. Before your classic summer storm, sunlight warms the ground and makes the air at ground level warmer than the air a couple kilometers above it. But before winter storms, the ground is already pretty cold and the more indirect sunlight doesn't warm it very much. So there aren't the same sorts of big temperature differences between layers in the atmosphere that there are in the summer. That might not sound like a big deal, but it makes all the difference in the world for both the type of storm and whether there's thunder. To understand why, it helps to know how summer thunderstorms happen in the first place. See, warm air can hold more moisture than cold air, so in the summer, water in the environment tends to evaporate into the heated air near the ground. That's part of why it feels so sticky and humid outside right before a summer storm. Then, those pockets of warm, wet air quickly rise into the cooler layers above them, and ultimately, the water condenses into these tall, dark storm clouds. Those jostling air pockets also generate lots of wind, another familiar sign of an impending thunderstorm. The wind whips up the water droplets and ice crystals and dust in the atmosphere, and as those different materials rub against each other, electric charge gets separated, with one part of the cloud becoming more positively charged and the other more negative. This is known as the triboelectric effect, and it's the same reason that you sometimes get zapped by static electricity. Eventually, the charges in the cloud get so out of balance that a lightning bolt streaks across the sky to even things out. That lightning superheats a column of air, which expands as it's heated and then contracts back together after the bolt is finished, and that vibration of air finally gives you thunder. It's a pretty specific series of events. You need warm, moist air rising through turbulent winds into cooler, drier air, and then that needs to generate the electric charge imbalances that lead to lightning and thunder. This happens all the time in the summer, but it usually doesn't happen in the winter because winter storms tend to fail at the first step of this process. Since the ground generally stays pretty cold in the winter, the air above it stays cold and dry. So any rising moisture tends to condense pretty uniformly throughout the sky instead of all in one place. Instead of the tall, dark, and handsome clouds that precede a summer storm, you get shorter, grayer, gloomier ones that cover the whole sky. And instead of electric charge building up, the charge is dispersed or hardly separated at all, so things tend to stay pretty quiet. But under just the right conditions, there still can be thunder during a winter snowstorm, or a thundersnow, to be exact. It sometimes happens near lakes or other large bodies of water, where the water warms the air right above it, just like the ground does in the summer. Thundersnow can also happen during a powerful nor'easter, a kind of storm along the eastern coast of the US. These tend to have strong winds that churn the atmosphere and can separate enough electric charge for lightning even in the winter. Thundersnow can be pretty alarming when it happens because we're so used to blizzards just silently raging while we huddle at home with our tea and hot chocolate. Still, it's definitely cool and it gets meteorologists pretty excited. There are even some viral videos to prove it. But even though we know the kinds of conditions that can cause thundersnow, scientists still don't quite know how common it actually is, so they're working on strategies to better figure it out. Recently, scientists have found out that if winter lightning is likely, the ice crystals in a cloud will all get tilted in a certain way by the electric forces in an impending strike. And that means radar will bounce off the clouds in the same way, which could help scientists track and predict thundersnow. So this winter, they've been looking carefully at weather patterns, radar, and even reports on Twitter to help us understand if thundersnow is coming to a blizzard near you.
We're lucky thundersnow isn't very common. Curling up by the fire to read your favorite book with some hot chocolate would be much less serene in a noisy thunderstorm. But if you'd rather watch YouTube videos, then you might like the SciShow winter compilation from a few years ago. Thanks for watching, and stay warm.